Many computer vision problems such as image alignment, 3D reconstruction, camera calibration, and many others are typically solved by optimizing a cost function. For instance, let us consider the problem of 2D point cloud registration. In this case, we are given a model shape and a target shape, and we want to estimate the rotation and the translation that align both shapes. To solve this problem, we minimize a cost function, such as the sum of the squared differences between the target shape and the rotated and translated model shape. Here, P denotes the assignment between the points in both shapes. In the case where the shapes have no noise or missing data, the optimum is well defined and coincides with the true registration parameters in the red diamond. In this ideal case, when starting with the initial pose in the green square, simple algorithms such as ICP can find the correct pose. However, in reality, the data is typically corrupted by noise and outliers, and this changes the landscape of the cost function. For instance, outliers can significantly increase the number of local optima, and ICP can easily get stuck in a bad one. Furthermore, if the target shape is incomplete, there might not be a local optimum that corresponds to the correct solution. As this simple example shows, there are several challenges when using optimization-based formulations to solve computer vision problems. First, it is unclear what is a good cost function for a given problem. Cost functions typically consist of 1. The data terms, which penalize the residuals from the observation, and 2. The regularizers, which control the behavior of the solution. But how do we know what functions should we use? For instance, the L2 and L1 functions are suitable for the residuals with the Gaussian and Laplacian noises respectively. However, the data may have a mixture of multiple and perhaps unknown noises. In such cases, using a non-optimal cost function may result in undesirable solutions. Second, many interesting computer vision problems are nonlinear in nature, and they are prone to having local optima. This makes solving for a good optimum a challenging task. Third, many optimization algorithms rely on the smoothness or differentiability of the cost function. Without them, more sophisticated algorithms may be required to solve the problem. To address these issues, we propose Discriminative Optimization, or DO. DO uses training data to learn a sequence of vector fields from the initialization to the ground truth solution. DO relies on the following update rule, where xt is the current estimate, h is a function that extracts some feature at xt, and the matrix dt plus 1 maps the feature to an update vector. The sequence of maps dt plus 1 is learned from a set of training data, and they provide the direction for updating our estimate. By following the update direction from the learned maps dt plus 1, we are able to update our parameter to the correct solution in training and testing. The maps dt plus 1 are learned from multiple training samples. In the example of 2D point cloud registration, they may include different rotation and translation, noise, outliers, incomplete target, and their combinations. The maps are trained such that the current estimates are forced to move toward the ground truth parameters. This makes DO robust to different perturbations in the data. Due to its simple formulation, DO can be trained and run efficiently on single CPUs, making it suitable for mobile application. In terms of theory, we provide the conditions for the convergence in training data and also propose a framework for deriving the function h for multiple problems. Next, we show a few applications of DO. Going back to the registration example, we can see that DO can obtain the correct pose under strong perturbations. By looking at the convergence region, we can see that DO can converge to the correct parameters from a much larger range of initialization than ICP. We also applied DO to restore images contaminated by impulse noise. It can be seen that DO does not oversmooth the edges and can retain high level of details. A single trained set of maps can also handle different levels and types of noise without requiring parameter adjustment during test time. In the next experiment, we applied DO to solve the correspondence problem. Given feature matches between two images, we use DO to solve for the homography transformation. As can be seen, DO is able to align the two images under a large number of outlier matches. Similarly, we can also apply DO to the problem of 3D camera pose estimation. In general, DO is faster and achieved similar accuracy as RANSAC. However, in extreme cases with large number of outliers, RANSAC is more robust. Finally, we used DO to track an object in 3D point clouds reconstructed from a depth camera without using RGB information. In this video, we can see how a Mexican hat in red is robustly tracked through severe occlusions and outliers. The method is very robust and efficient. In a single thread, the MATLAB code takes 40 milliseconds per frame. Thank you for watching. If you are interested in learning more about DO, please check the following CVPR paper. An extended version is available in the following arXiv link.